Hello everybody, welcome back to another Gregorius Maths video. Today we're going to be looking at compactness. As in the last video on connectivity, we're going to be looking at a theorem which, when proven, will motivate why compactness is important in topology. So, if we take a look at another theorem that topologists like to prove. Okay, so any continuous map F which takes you from the closed interval between 0 and 1 and maps onto the reals is bounded. Okay, what this means is there exists J and K such that J is less than f of x is less than k for all x in the domain. Okay? So, now we're going to take a look at some rough work before we finish off the proof. So, proof. Okay? So, consider what we call an open cover of the real line. So we have some open sets. We have the open sets, open interval 0, 2, 1, 3, 2, 4, etc., etc. Well, all of these open sets form an open cover of the real line because they're open subsets of R, and every point in the real line is covered somewhere in here. Okay? So, because of this, and because all of the pre-images are still open, that means that the pre-image of I, the open interval between I and I plus 2, for all I in the integers, form an open cover of the domain, the closed interval between 0 and 1. Okay? Now, if f is bounded, okay, this means there exists J and K such that, okay, the image of F is completely contained inside of the union of all of these open intervals. Okay? Or in other words, the closed interval between 0 and 1 is this, the pre-images form an open cover, okay, of J plus union the pre-image of this open interval union the pre-image of this open interval. Okay? And what this is called when, okay, so now we lay the definition of compactness. Okay? A topological space T is compact if, okay, given an infinite number of open subsets of T, okay, we can discard most of them. Okay. Leaving us with, so that there are only a finite number of them. Okay? So, in other words, all that's left to be proven is that the closed interval between 0 and 1 is compact. Okay? So, in fact, we've pretty much shown that any function which goes from a compact space to the real line and it's continuous is bounded. Okay? Okay, so let's just write this down. Proposition, let's call it. Okay, so now that we've reduced the problem down to just proving that the closed interval between 0 and 1 is compact, let's prove it. Whee! Proof. Okay, so for the closed interval between 0 and 1 to be compact, we can split it up into two different subsets. So for example, the closed interval between 0 and a half, and the closed interval between a half and 1. And if they both admit a finite refinement, okay, that means that the whole thing admits finite refinement, and hence the closed interval between 0 and 1 is compact. But assume that this is not the case. That means that one of those two closed intervals must not admit a finite refinement. Let's call this I1 and use the argument which can be repeated for the other closed interval, completely the same. Let's just call I1 the closed interval between a half and 1. So I1 equals the closed interval between a half and 1. And this admits no finite refinement. Okay? Now, using the same argument, we must be able to split this one in half again. Call this I2, and it has no finite refinement. It's equal to the closed interval between 3/4 and 1. Okay? Now, we can carry this process on of splitting and splitting it and splitting it, okay, again and again and again, leaving us with this complete infinite chain of subsets, I guess. Yeah. Okay, something like this. Now, IN has length 1/2 to the power of n. Okay? Now, if we intersect all of the I sub n's, okay? So now if we take the intersection of all of the I n's, we get C in the closed interval between 0 and 1. Okay? Since C is in the open cover, there must be some finite refinement. There must be some breathing space around C. So there exists some delta sub C greater than 0. Okay? Such that, okay, basically this gives such that this is breathing space, I guess, around C. Okay? Now, for n large enough, namely n greater than log base 2 of 1 over delta sub C, okay? Let's just say for n large enough, okay, fine, you persuaded me. I will write how large n has to be. Okay, for n large enough, I sub n will be contained in this open interval here. Okay, this is the point at which we have fun, because this implies I sub n has a finite refinement of the original open cover but I sub n was chosen not to have a finite refinement, therefore we have a contradiction. The closed interval between 0 and 1 is compact. Okay, and therefore we have proven that every continuous map f from the closed interval between 0 and 1 to the real numbers is compact. Okay? Now, I'm not going to beat around the bush. I'm just going to go to the big theorem, which is very, 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 very helpful. Like, super, super helpful. Like, I can't begin to express how helpful this is. Okay. At least for compactness. And this is the Heine-Borel theorem. Okay? And it's just so goddamn important. Okay, so yeah, we're going to prove the Heine-Borel theorem. Okay? So what it states is that T, a subspace of Rn, is compact if and only if, okay, T is closed and bounded. Okay? This is just so useful. Now I'm only going to do the partial proof. Okay? Because I'm going to leave half of the proof as an exercise to you, because someone in the comments requested that I leave some practice questions, so yeah. Okay, so let me just do the partial proof. So if T is closed and bounded, it means that T is compact, and I'll leave it to you to show that if T is open, T will not be compact. And if T is not bounded, then it's obvious that T is not compact. Because, for example, if we have the real line and we define I sub n to equal this and etc, etc, basically it's very obvious to show that any non-bounded space is not compact. Okay? So, for clarity, we'll just prove it for the real line, but it's very easy once you know how to do it for the real line to prove it for Rn. So, first of all, we'll state that if T is bounded, that means there exists A and B in the real numbers such that A is less than X is less than B for all X in T. Okay? Now, if T is closed, okay, recall from the first video where I briefly mentioned this, okay, that means that the complement of T, okay, is open. Okay? So, in the subspace topology, okay, in the subspace topology, for example, the intersection of T with an open subset of the real line is open. Okay? Now, taking these subsets together with the complement of T, okay? So taking these subsets together with the complement of T will cover R, okay? So now, okay, so if we intersect these open subsets, okay, and this includes R minus T, the complement of T, okay, with the closed interval between A and B, okay, these bad boys here, okay, if we intersect these subsets with the closed interval between A and B, they will cover it. Okay? However, we proved that the closed interval between 0 and 1 is compact, but it's fairly obvious to just modify that proof slightly to show that the closed interval between A and B is compact. Okay? That means that there is a finite refinement of the open cover. Okay? So there's a finite refinement of this open cover. Okay? Now, intersecting. So now when we intersect this new open cover with R, the real line, with R, okay? So when we intersect this open cover with R, we get a finite yeah, we get a finite refine. Sorry. So we did the finite refinement of the open cover. Oh, sorry. We don't intersect this with the real line. Sorry, I knew that was wrong. Open cover with T, it will certainly cover T, okay? And it's a finite refinement, because the only extra set we added was the complement of T, and when we intersect that with T, we get the empty set. Hence, T is compact. Okay, so exercise is to prove that if T is open, then T cannot be compact, and if T is not bounded, well, that's easy to prove. Okay, that's like one line. Okay, so a quick corollary that we have is that the N sphere is compact. Okay, the open interval between 0 and 1 is not compact. Okay, the real line isn't compact. Okay, also, there is no continuous surjection from the open interval to the closed interval. Okay, because the image of a compact space is always compact. Okay, so yeah, there's a lot of implications of this theorem, especially in compactness specifically. So if you know this, and preferably you know the proof, okay, then just refer back to it why am I rubbing out the proof? Dang it. I kind of wanted to look at it while I was sleeping, but fine. Okay, so if you know this Heine-Borel theorem, you should be good to go when talking about compactness. So if someone wants to prove that the closed interval between 0 and 1 is closed, for example, just say, hey, that's a consequence of the Heine-Borel theorem. Goodbye.